work is on the security of Schnorr signatures. We're going to study the, I don't know if you heard of it, but like tight security of Schnorr signatures. It's joint work with my student Gavin Cho and also Georg Friesbach at TU Vienna. So, so the background is just briefly signature scheme. The signature scheme, Schnorr's signature scheme, is derived from Schnorr's identification protocol via the Fiat-Shamir transform. That's just some conceptual background. You don't need to know that for the purposes of this talk, but that's how it came about. They're one of the most widely deployed pieces of cryptography today, and they're used all over the place. Here's just some examples. And you can actually go to this. Oh, I can't. It's putting in the, well, anyway. You can go to this website and there's like hundreds of examples of where it's deployed in the real world. Okay, so now let me just directly define the scheme. I guess I didn't have the definition of signature scheme, but you can tell what it is based on how I define Schnorr signatures. So Schnorr signatures use a cyclic group of prime order and big G, and it's generated by little g. Okay, and it uses also a hash function, which maps a group element and a bit string, which will be the message, to an element in ZP. So you can think of this using a cryptographic hashing for this, like a SHA-256. It's usually. Okay, so so here are the algorithms of the Schnorr signature scheme associated to G and H. I've just given them in boxes here. So the key generation is very simple. It just generates like a discrete log challenge, right? So G to the X, and then the signing algorithm is randomized. So it chooses a little r and exponentiates to get big R. That hashes the R. So you can think it like if you think of it as like in terms of Schnorr identification protocol, you use like the hash function to generate a challenge. So R is a commitment, C is the challenge, right? So C is computed as the hash of R and M. And then you compute S, which is equal to R plus C times X mod P. And there's a simple verification check that you can make. Right, so this is like a very simple, one of the nice things about this work is that like the scheme is extremely simple, right? So it's not hard to think about the security. Okay, so what's known about Schnorr? So it's been intensively, it was introduced in 1990 or something like that. So it's been around for some kind of like 35 years. It's been studied a lot. The drawbacks of the current state of knowledge are that positive results all rely on the random oracle model. So you need to model H as a random oracle in order to prove anything about its security. Okay, I'll define random oracle model in a bit. But I like how you emphasize artificial. Yeah, yeah. So, and then even in the even in the ROM, even in the random oracle model, there's a large gap between the known upper and lower bounds on its security. So like the running time of the best attack differs greatly from the running time of, like, the running time of attacks we can rule out by a proof, right? So we'll see concretely what that means. This is our focus. So we're going to focus on security in the ROM, but on closing the gap between the upper and lower bounds on the security of Schnorr. And yeah, so the main question is how hard is it to break Schnorr in the ROM? Okay, and I mean, just, yeah, like ideally you want that it's as hard as breaking discrete log, right? But it's hard to prove that. Okay, so just to give, and then like you don't need to know exactly what this means, but I just wanted to give like an overview of what our results, so you know where this talk is heading. So we give a tight reduction from unforgeability of Schnorr signatures to a new problem that we call circular discrete logarithm. So the best result here would be to give a tight proof under discrete log. We introduced like a slight variant of discrete log and give a tight proof to that. So we don't kind of like close the story on the tight security, but we get closer. And then we give a we analyze our new assumption in some idealized models. So we give a proof that this circular discrete log is as hard as discrete log in what's called the elliptic curve generic group model. And also we use something called the algebraic bijective random oracle model to give another proof that like this idealizes a different aspect of the assumption. And it's again like evidence that circular discrete log is as hard as discrete log, right? So like we want to avoid additional idealized models beyond the ROM to analyze Schnorr itself. But then when you analyze the underlying simple assumption, like we do use idealized models for that. Make sense? Okay. And yeah, so I'll explain what all of these things mean. This is just to give like an idea of what's happening. Okay, so I guess everyone probably knows this, but I'll define discrete logarithm problem. So yeah, I write everything in like these games. So I don't know if you've seen this with like initialize and finalize procedure. So initialize generates a challenge for the adversary, and finalize checks its output. So it just checks if x is the output, x prime is the output of the adversary. It checks if x is equal to x prime, and x is uniquely determined, right? So there's only one solution. Okay, and then the advantage is just the probability that this game outputs 1. So the probability that the adversary recovers discrete log. And now I define security of Schnorr signatures. So this is also standard. I just write it here. So the way the game works is the initialized procedure generates like a public and private key and gives the public key to the adversary. And then the adversary can call a signing oracle on messages of its choice and gets back signatures. The finalized procedure checks that the output signature is valid and that it's fresh, meaning that the signature wasn't returned by the signing oracle.
So the M is the input of the adversary. It's finalized, right? So
yeah, so the whole finalized procedure is the output of that. The input to the finalized procedure is the output of the adversary.
Okay.
So outputs R prime, R star and S star as it's like purported forgery. And then M is the forged message. And then, yeah, you define advantage in the obvious way. It's just very simple. Any questions about this? You guys are okay? Okay, so now I just want to go through everything so that in case anyone doesn't know. So a random oracle model, this is like an idealized model of computation for cryptographic hashing. So in the random oracle model, all parties have oracle access to the same random function, which is supposed to model a hash function. Okay, so it's kind of like a perfect hash function. So the way it looks is like different parties can query this box, which as a black box, they query it. And like if Alice and Bob query it and they have the same inputs, they get the same outputs. Otherwise, they get independent random outputs. Make sense? So, okay. So maybe you don't know this is a like somewhat. I mean, maybe you haven't learned about this. So tightness of a security reduction, it's a quantitative metric of the quality of a reduction, right? So how like we don't just say that like you have a reduction or you don't have a reduction. You can say like how good is the reduction. Okay, and to illustrate, so I won't define tightness in general. I'll just show you what I mean by giving you example for Schnorr. So let's study this is a classical result of, so actually I guess when Schnorr was first proposed and used with Fiat-Shamir, there was no security proof. So it came only in '96 by Poincaré and Stern that they had a security proof in the ROM. And they gave this theorem. So let me explain the theorem. So it basically says that if there's an adversary A against Schnorr in the ROM, there's an adversary B against discrete log in the underlying group with this advantage relation. So it's saying that like the the forgery probability of A is bounded by like QH, which is the number of hash queries it makes, times the square root of the discrete log advantage of B plus some extra term, which you can kind of ignore. So the thing that's damaging here is like the QH and the square root. So let's see what this means. I'll give you a minute. This is from the, I mean, I'm not going to cover it, but this is from the forking lemma. So like use the forking lemma to run. That's why it says you run the adversary twice, and that's why you get the square root, because you have to like, you fork it and run it again, and then it has to succeed twice. So you got to square the advantage. And that's the, like the main problem here. Okay, so here's a question. Suppose we want to implement Schnorr on twisted Edwards curves with 128-bit security. How large do we make the group order? Like how many bits would the group order be? Yeah, yeah. So that's what you would think, right? So that's indeed the view of practitioner, right? So the best attack on a twisted Edwards curve of or the order, if the order has 256 bits, is 256 bits, the best attack is time square root of the order, right? So it's time 2 to the 128. What we'll see is that the consequence of this Pointz-Stern result is that in order to deduce 128 bits of security, you would have to actually set the group size to 768 bits, which, I mean, practitioners would never do. It's very kind of artificial. Everyone expects that it should just be 256, but the question is, can you prove that? Okay, and so I'll go through the calculation of this 768. But do you see the claim? Like I'm saying if I assume that like the best attack on a discrete log for like appropriate twisted Edwards curve is square root of the order, then what I get by the Pointz-Stern result is that you need 768 bits for 128 bits of security. You need a 768-bit order for 128 bits of security. No, they just have a loose proof, right? It's because we're just ignoring the other terms. No. So
they have what?
they have a they give a proof that like if you assume, so if I assume, I'll go through the calculation, but
specific for this case.
No, like if I assume that the best attack takes square root of the best attack on discrete log takes square root of the order,
right?
Then it follows that to use their proof, you need 768 bits to get 128 bits of security. Because let me go through the calculation. So yeah, who was right? So twisted Edwards curves like are conjectured to have k over 2 bits of security when the group order is 2 to the k. So plugging in 2 to the minus k over 2 for the advantage of B, right? And taking QH says 2 to the 64 as a common value that people like use for these bounds in practice. We get the forgery probability of A is at most 2 to the 64 minus k over 4. And so what you have to do is you have to set, in order to get so you have 2 to the minus 128 equals 2 to the 64 minus k over 4. So you set k to be 4 times 192, which is 768.
So this holds when you use the scans for the Schnorr signature.
Yeah.
This is okay.
Yeah. So if you use a curve where if you assume the best attack is generic, and you want to apply the Pointz-Stern result, you need a larger group order than what you need to rule out the best attack, right? Because it's basically like we don't know a better attack, but we don't know that a better attack doesn't exist. I mean, we can't prove it, right?
Basically, if you put 256 and you plug it in this formula, then you're gonna get really bad security, right?
Yeah, then you get 0 security. So it doesn't give you anything. Yeah. But I want to stress that after 3.5 decades, the best attack on Schnorr signatures is breaking DL. So we think the right answer is like you would set it to 256, right? yeah, so indeed, like, I guess I'm kind of repeating myself here. So from a cryptanalytic perspective, practitioners simply set 250 to 256-bit order. And in fact, the PS96 proof is vacuous for such parameters. It gives you 0 bits of security. So they don't have a real attack, no, but they don't give you any guarantee, right? Like we want a provable guarantee. So the main question we study is, can we show a tight security proof for Schnorr signatures? Meaning like, I mean, in this advantage relation, we want to eliminate the QH and the square root, right? That would be a tight, basically a tight reduction.
Right.
So this is a long-standing, to do this under discrete log is a long-standing open problem. Let me just talk about what are the prior results towards this goal. So I list here some results in a table. The Poincaré-Stern, as we've seen that it's under discrete log, but it's not tight. And interesting result of Pallier and Vanguard is that they don't use the ROM, but they only prove security against key recovery. So not full unforgeability, but they give a tight reduction under what's called one more discrete log. So it's like a very much stronger assumption than discrete log, where you have an oracle that solves discrete log for you on like other points than the challenge. Then there's also Bellari and Dye had they give what I call a semi-tight reduction. I mean, they tighten the security compared to Poincaré and Stern, but it's still quite loose. So they kind of went halfway, kind of thing. They use.
How do they change the formula? The QH.
They eliminate the square root.
Oh, right.
Yeah, yeah. So they don't use the forking lemma, but they use a new assumption called multi-base discrete log, which is similar to one more discrete log. And then if you use the algebraic group model, you can prove a tight reduction. But we like to avoid the algebraic group model for the scheme. And then there's a recent result of Rotem and Segev. They use something called high moment discrete log, where they tighten the proof a little bit, but again, it's still not very tight, but it's a little tighter compared to it's like the initial result of Poincaré and Stern. Again, so what I want to emphasize is like the salient point is that right now, as things stand, getting even a semi-tight reduction requires interactive and non-falsifiable assumptions. So we don't know, I mean, until this work that I'm presenting, we don't know any tight, even a semi-tight reduction that significantly improves upon Poincaré and Stern. Under anything which is like either falsifiable or non-interactive, like it requires all these assumptions I've circled here are interactive and non-falsifiable. So what does that mean? So interactive means the adversary has oracle access, so it's like can ask questions and get back responses. In one more discrete log, for example, like I think the way it works is it gets a bunch of challenges and can ask for discrete logs for some of them. Like, so you get like a vector of discrete log instances. You say like, okay, give me the solutions for like these ones, or maybe not that. What is this assumption? Something like you can. I mean, the point is you can ask for discrete, like the adversary in its quest for solving the discrete log instance could ask for the discrete log of some other points subject to some restrictions. I forgot the exact assumption, but it's not that important. It's much stronger than discrete log, right? Because the adversary can create this oracle. It's like more power to the adversary.
Oh, okay, got it. So, right.
Mm-hmm.
You get the discrete logs.
Yeah. So it's bad because it's very complicated. Well, I'm going to say it, but it's complicated to cryptanalyze. Like if you want to say, like if you want to tell a cryptanalyst, like, can you please cryptanalyze this assumption? Like discrete log is very simple. They could probably try to do it, but like one more discrete log, that's quite hard to know, like what's the best attack. It's not very natural for a cryptanalyst, basically. And then non-falsifiable means that it's not possible to efficiently prove that you found an attack. So like typical, basic assumptions in cryptography, you have this property called falsifiability. Like if I give you a factoring challenge, you can prove that you can you can prove to me that you have a fast factoring algorithm by me giving you a challenge and you telling me the factorization, right? So we call it falsifiable, but like more advanced assumptions are not falsifiable. And the reason why these ones that I circled like are not falsifiable, like in this setting of one more discrete log, like the game is not efficient because it has to compute discrete logs for the adversary. So like if you claim that you have an attack against a one more discrete log, like I can't even run the game to verify that. So
all of them are not.
Yeah.
All of them.
Yes. Yes.
I guess for the interaction though, in the real world, isn't that better to have an adversary that can not break the discrete log even after?
But it's a stronger assumption, right? You're saying that like I have to assume that even if the adversary, this like more powerful adversary can't break discrete logs, so it's a stronger assumption, right? Any questions about this? Yeah. So they changed the 1/2 to a 3/2 or something like this. And they use this thing called high moment discrete log, which is basically you assume some bound on the expected like the adversary's advantage is like tightly concentrated around the mean or something like that. I don't remember the exact formulation of the assumption, but it's something like some additional assumption on how the adversary's advantage behaves. Okay, and then yeah, my point is that basically if you use these kind of assumptions, they're hard to cryptanalyze, which I already mentioned, and proofs kind of move toward tautologies because like if you think about it, you can certainly prove Schnorr is secure under the assumption that Schnorr is secure, right? And that's an interactive assumption. So if you have an interactive assumption under which you prove Schnorr is secure, it's not clear what are you gaining over this trivial statement, right? I mean, formally speaking, it's not clear what you're gaining.
How often is this true? Like if you add, like is this also true for assumptions that allow you to do that if you added interactive oracle access, it becomes non-falsifiable?
If the oracle is not efficient, it is non-falsifiable, right? So the problem for these assumptions is that the oracle the adversary gets has to compute discrete logs, and so it's not efficient. If you had an oracle, like I guess like if you want to consider like for example the assumption that Schnorr is secure, I guess it would be falsifiable, right? Because I can run the game with you and I can answer your queries and see if you forge. So maybe it's not always the case. Okay, good. So interestingly, there's like I don't know how well known this is. There's like an interesting sequence of works on negative results for this problem as well. So kind of the culmination of this line of work is that they prove that there's no, this is like a complicated statement, but a tight and generic reduction from a representation. So if you want to reduce I think I mixed up, like it should be tightly reduced Schnorr signatures to the assumption. I flipped it by accident. But what did I say? Yeah, so they prove that if you want to reduce, say I want to give a tight reduction for Schnorr to some underlying problem, right? Like discrete log, for example. They prove you cannot do that if the reduction is what's called generic. Generic means that the underlying group is treated as a black box by the reduction. And also the problem that you're reducing to is what's called representation independent, which is an interesting property. It basically means that if you change the underlying representation of the group, a solution to the problem remains a solution. So like if you think of like every group of order P is isomorphic, right? So in some sense, it doesn't matter what you're using, but when you talk about like computation, it matters, right? And like suppose I have a discrete log relative to some point in a twisted Edwards curve, right? if I change the group representation, it's still going to be the discrete log of the same point under the new representation of the group, right? Like it doesn't affect the fact that this is a solution to the problem. That's not the case. I mean, we'll see that's not the case for every assumption, but they prove that like, I mean, the problem is now that like all the common assumptions that we use are representation independent. And this kind of says that like if you're using a representation independent assumption, you run into a problem, which is kind of more fundamental than like I mean, it's yeah, like it. We're going to consider. So I mean, the question we ask is, I mean, broadly speaking, we ask, is there a representation dependent assumption or a non-generic reduction that gets around this impossibility? So like, can we bypass this impossibility basically by using either a non-generic reduction or a representation dependent assumption? It's even hard, like when we started this project, I guess it's like hard to even imagine what a representation dependent assumption would look like, right? Because it has to depend on how the group is represented in bits, which seems kind of unnatural. So that was like, but that was like the starting point for the work.
Refers to specific implementation of the group.
Yeah, so it says, it's what it says is that like, if I know a solution relative to one representation,
Right.
and I change the representation, I may not know a solution to the under the new representation. So like if I have a discrete, like think of it like g to the x, I have say I know x, right? No matter how the group is represented, that x is the solution to the discrete log problem, right? It doesn't matter.
Yes, yes, yes.
Yeah, so that's representation independent.
Right.
And then a representation dependent would say like if I change the representation of the group, this may not be a solution anymore.
There exists an X such that it will be a solution, or is it with high probability? Or?
No, so like okay, so the formal definition is like we say a problem is representation independent if like a solution, so a solution under one representation of the group, and then I switch the representation, it's still a solution in under the new representation. That's what it.
So basically, if there exists any.
If there exists.
Any case where it's not.
Yeah, if any solution maps to like a non-solution, then it's not representation independent.
What is like? Can you just repeat what generic means?
Yeah, so it just means that the reduction itself doesn't care what the representation of the group is. It only like it can operate with respect to an oracle for the group. Like it can just ask like what's this element times this. It doesn't care what the bit how the bits are representing the elements.
Previous reductions were not generic.
They are generic. Yeah, like the Pointierwall-Stern is generic. Yeah, I mean it's also hard to imagine how the reduction would not be generic with respect to the group, right? Because it seems like anything which, yeah.
How do you capture mathematically the representation? Like, is it the function?
Yeah, it's a good question. I guess it would be a mapping. You could say like if I have represented in terms of its discrete log. So I map a discrete log to a bit representation of the g to the, like I map x to a bit representation of g to the x. If I do that for all of the ZP, then I have a representation of the group.
And then you change the function.
Yeah, yeah.
Like, okay.
Yeah, exactly. Okay, so so let me tell you like our solution to this problem. So here's a new assumption. So I'm gonna define it relative to a function f. So the assumption is not gonna just be in terms of a group, it's also gonna be in terms of some function f. And you can think of f as a very simple function, not like a cryptographic hash, but maybe I'll put some bits of its input or something like that. So I have a function f from G to ZP. And the game for CDL, I have, just to compare, I have discrete log on the left, but on the right, the adversary gets a discrete log instance, and it has to find a solution to this equation. It has to find a solution to, it has to find R and Z such that G to the Z is equal to R times H to the F of R. Yeah, and the name circular we chose because R is in the base and the exponent. So it kind of the base and the exponent kind of depend on each other. You find a group element and a ZP point.
Map to 0 such that R
G to the Z is equal. And I mean, this is, you can see like that's obviously comes from the Schnorr verification equation, right? But like it's a much simpler problem than forging against Schnorr because now I'm considered like actually like our proof doesn't even care what F is technically. It just cares that some F exists for which this problem is hard. So if I have a group, like if I have a twisted Edwards curve and I say like my assumption is there exists some F that makes this problem hard for the group, then our reduction is tight. It goes through. Like if the F is only used in the proof, basically, it's not used by the scheme. It's a function, yeah. It's an efficiently computable function.
The adversary doesn't have access.
Adversary, it's public, yeah. Adversary has access to it. So adversary knows F and it gets a challenge G to the X, which we call H, and then it needs to find a solution to this equation. Mm-hmm. Yeah, if any F is any, yeah, if you find like, if you have a group in mind that you want to use Schnorr for, and you find some F that makes this problem hard, I can give you a tight reduction to
oh, I thought F is fixed. F is just
yeah, it's your choice. I mean, the assumption is parameterized by G and F, right? So I'm saying like if you have a G and there exists an F such that this is this assumption is true for G and F,
right.
Then I can give a tight reduction from what can I give it? Yeah, tight reduction to CDL. Yeah.
Intuition is that this is supposed to represent representation dependence.
Yes, so it's good. So this is representation dependent because little f cares about the bits of the input, right? If you change the group representation, f of r will change, and it may no longer be a solution to the equation.
So f is kind of like your assumption on how things depend on their representation.
Yes, yeah.
Can you give like an example of something you believe?
Yeah, so we analyzed the EC DSA conversion function. So like imagine you're working with elliptic curve, like twisted Edwards curve. So a point in the curve is like some XY coordinates, and the f just outputs x.
So what's that? Just
yeah. So say like I'm working an elliptic curve. So my points on the curve are some x comma y.
Right.
And f given x y just map to x.
To x.
Yeah, because that's an element in ZP, right? So.
And you can also
yeah, we prove in like in the GGM or the generic group model, like this is hard for this. I mean, we have to use elliptic curve GGM for some reason, but I'll explain it.
You have another example which is not part of the input. That's different.
Which is not part of the input?
Yeah, like the output is not part of the input, right?
Oh, I see. Well, you could take a cryptographic hash, for example. But I kind of are like, we wanted to say that like the function can be much simpler than that. But yeah, you can take a cryptographic hash. In fact, I think it's necessary that a cryptographic hash would satisfy this function for Schnorr to be secure in the standard model. So like if you replace a random oracle with a concrete hash function, if that hash function didn't satisfy the CDL assumption, I think Schnorr wouldn't be secure.
So if this assumption is true for a specific f, you can't prove that DL is hard, right? You have this implication, right?
No, it's not. So we reduce the if
you cannot prove equivalent to DL, I guess.
No.
Right.
Yeah,
but you can prove from this to DL if this is
yes.
Right.
No, so I proved from Schnorr to CDL. From CDL to DL is not known. So yeah, but one interesting thing is that it could be like given these impossibility results, it still could be possible that there's a reduction from DL to CDL, right? Because like it would seem to be you would get by composition, you would then get a reduction from DL to Schnorr, right? And you're then reducing to representation. I mean, you're then reducing to a representation independent assumption, which is DL, right? But it would still get around the impossibility if because the reduction would compute F, so it's not generic. Okay. So yeah, that, and then yeah, these things. So CDL, you can just check that it's not interactive, falsifiable, and the representation dependent.
Sorry, X, we actually, doesn't the representation matter for the value X as well?
Little x? No, that's just ZP, right? So ZP stays like that. It's just the integers mod P. Yeah. Okay. So so this is our like main result that you can see here. I mean, basically compared to the Poincaré and Stern, we eliminate the square root and the QH on the advantage of B. Right, that's it. That's like the main difference. And I actually, an interesting thing is that like the tightness of the reduction does technically depend on the running time of F. Like if F is astronomically inefficient to compute, it would like not give a tight reduction. But all the Fs that we consider are like very simple, so it doesn't affect the tightness.
Yeah. This one outputs the X.
Yeah. Oh yeah, so that's the preimage set. It's interesting. So this is something interesting that comes out of our proof, which is the quality of the reduction depends on the size of the inverse preimage set of 0. Kind of like the problem is that like if F has too many things that map to 0, we're kind of likely to extract out a CDL solution where F is mapping to 0, and then that's not allowed by the like we don't win the game.
But for a curve, it's 2, right?
Yes, exactly.
Right.
Yeah. F needs to be efficiently computable, yeah, because it's computed by the reduction. So it's any efficiently computable mapping.
But not by the scheme. You don't need.
No, the scheme doesn't change at all.
I see.
Yeah, it's only in the proof. So we only use F in the proof.
Oh, that's interesting.
Yeah. Yeah, so actually, if you, yeah, I didn't mention this, but you have to have some sort of like approximate regularity to F. Like in order for it to satisfy CDL, if there's a point that F maps a lot of inputs to, too many inputs to, you can break CDL. So yeah, that's a good point I didn't mention. So actually, beyond the fact that the preimage set of 0 is sufficiently small, you need like the preimage set of any element is sufficiently small. That doesn't come up in the proof because like our proof doesn't care about that because like you just be then reducing to a false assumption. So it's still true. The proof is still true, but yeah.
F is not generic, right? You have to have some properties.
Yeah, so F is like F, the output of F depends on the bit representation of the input, right? It like reads it as a bit string.
So if you have an F like Arthur mentioned, then you can break this assumption with the circle the CDL.
Which F?
So if F maps to 1 all the time.
Yeah, you can
CDL
break it.
is
Yeah,
generic,
you can
right?
break it.
You can
Yeah,
break this.
yeah. So the preimage sets can't be too large.
Right.
Yeah.
Because you can then just get a different output. It's a mathematical isomorphism where the ones map to
Mm,
you can
the reason is because there's an attack. There's like an explicit attack in this case. So the attack
But
is.
you can always reduce it to the 0 problem. If like if you have any element that is
Oh, by just relabeling the points.
Mhm.
Is that true? That might be true. Yeah, I didn't think about that. Maybe, yeah. So
Why does the TF show up in the movie?
TF does, it shows up
Right, yeah.
yeah. So the amount of times you compute F is proportional to the hash queries of the forger. Everyone good? Okay, so it's actually like I mean, this is, I feel bad because this is like a very simple proof, but It's like leading, you feel like you're leading up to something really deep, but then it's pretty simple. So I'll go through the proof.
It makes it better.
Yeah. Not according to reviewers, but it's so here's like I'll sketch the reduction. Okay, so we are going to run the forger with the public key, which is equal to the challenge. Okay, so this is called, I think in the literature, this is called like a canonical reduction or something like you just feed your challenge as the public key to the adversary. And signing queries are not changed compared to the original proof. So signing queries use programmability of the random oracle, and we do the exact same thing. What changes is how we answer the hash queries. Intuitively, in the hash queries, we want to embed outputs of F such that the first thing is that the forgery cannot detect these embeddings, so it looks like random values.
Random 8 is G to the X is the public key.
Mm-hmm.
Okay.
And then this is delicate because F may not be like F may be very skewed, right? So, and then the forgery, when the adversary forges, we can extract a solution to CDL from the forgery. So we kind of want to blind the values of F in the hash answers, such that when the adversary forges, we can strip off the blinding and get back a solution to CDL. Right. And yeah,
So is it a program?
Yeah. To answer the signing queries, you need programmability. Yeah, I don't know. I don't think without programmability you can prove Schnorr.
Even the null-type reduction use programmability.
Yeah. I think maybe there's some negative results for that. I'm not sure, but it's a good question. What you can do in the non-programmable random oracle model.
It's considered a stronger assumption of programmable.
Much stronger, yeah.
Much stronger.
Yeah, in fact, I mean, if you think about it, it makes no sense in practice, right? Because you're saying like
Exactly.
you can choose the.
Actually, I was trying to explain this to a practitioner when I was doing a postdoc at Berkeley, and they were looking at me as if I'm
Yeah.
from a different world.
So it's kind of like it's pretty strange. Yeah, I mean, it's not clear at all what it means in practice, right?
Really weird.
Because it's one thing to say the hash values look random, but then like it's another thing to say you can choose the outputs of the hash values.
There are a couple of papers on programmability. I'll send them.
Yeah, but I don't know what's been done for Schnorr. And I mean, I suspect there may be a negative result. I know for like full domain hash, there's negative results in the non-programmable random oracle model. I suspect if there's not a impossibility result, that could be interesting to prove for.
Did you say there was one work that did bounded algorithm?
Yes, but that's only it's good. That's only key recovery attack. So if you try to get something for full-fledged unforgeability, I think there's no proof in the not NP ROM known. Yeah, that's a good point. Okay, so this is what we do. We basically, when the adversary makes a hash query R, comma M, we compute this R prime, which is R times G to the AI times H to the BI for random AI BI. And we return the value F of R prime plus AI mod B. So that's how we answer the hash query. And basically what's going on here is that
People do the classes both R and M.
Oh, that's how it works in Schnorr, right? So we're reducing we're proving security of Schnorr, right?
So,
Yeah.
okay,
Yeah. So yeah. So does it make sense? And then I mean it's really simple to just check. Oh yeah. So this is not I'll just make a point here. This is our reduction is not generic because it's computing F. And now we can basically just simply show by some simple algebra that if the adversary forges, say the jth hash query corresponds to his forgery, right? Then we multiply both sides by bj and we get this equation, right? And then it's covered up. I don't know how to make that, but yeah, so you just have a solution to CDL here. So this is like a very, I mean, I think that there's like, there's a lot of open problems in this space. I mean, this is a very simple reduction, but I think maybe like, could maybe improve on the assumption or something like that.
I guess quantum reduction is simple, is great. The question is how to, I guess, like how to remove the program around the molecule.
That's not known. That's not known, right? I think that would be very interesting to prove that. I mean, we should check actually that if it's been proven, because it would be interesting. Yeah.
What's the problem with the random molecule that you need the
Programmability?
share, like even for the random molecule in general, I would say you need to share the random source that you can check.
Well, it's just to model a hash function, right? So like in practice, you just use a hash function. Or what? Sorry, what's your question?
The question is, what if you, okay, let's say instead of the ROM you have a source of randomness? That's not enough.
Well, but no, because the parties have to be able to like in isolation compute the yeah.
Do you need something to model?
Yeah, so this is actually like this has been proposed like implementing the random oracle by like a random beacon that I mean like a server would answer your queries, something like that, but it's kind of
You need the trust server.
yeah, definitely, yeah, definitely. So it's kind of silly, but I mean people have proposed it.
But then
Okay, cool. So now we want to basically move to studying the underlying assumptions. So we want to give some justification for why is CDL a valid assumption. So for the rest of the talk, we consider a specific F, which is the ECDSA conversion function. I mean, if you don't know ECDSA, it doesn't matter. This is the function that they use. Okay, and then the question is, can we prove CDL holds for F ECDSA in say like your favorite elliptic curve group? I mean, twisted Edwards curves or something like that. Okay, this seems challenging in the standard model, so we justify this assumption in idealized models. Okay, and interesting thing here is like standard idealized models, like if you're familiar with generic groups and algebraic group model, they don't work here. Why? Because, well, GGM has no notion of coordinates of a group element. It's just a random string. So if you output the x coordinate, doesn't make sense to do that for a generic group element, right? And then AGM does not allow, there's some restriction, it does not allow mapping group elements to bits. So you can't even model the assumption in the AGM. It's not allowed. Because I guess the reason for this is like technical, this restriction. It's like, I don't know, you guys familiar with it? There's like a line of work studying this, like refinements to the AGM, kind of where they clarify this restriction or something like that. But anyway, it doesn't work out of the box, at least.
yeah, whenever I would learn about it, I call Julian, that's what I understand from the meeting and then I forget.
Yeah, I mean, the intuition is clear, but formally defining it is a bit tricky. Oh, F is this function.
So the problem with using these models is because of the F function.
Yeah, so the F function doesn't work with the GGM or the AGM. Yeah, that's exactly right. So the two models we consider are what's called the elliptic curve GGM, and then something a little bit more technical called algebraic bijective ROM. So I'll explain what those are. The elliptic curve GGM is pretty intuitive. It basically means that like it's like the GGM, if you're familiar with the GGM, but the labels for the group elements are elliptic curve points. So you like an element is labeled with a random elliptic curve point, kind of. So it does make sense to take the x coordinate of this label. Yeah, so this it just, and then the encoding obeys some trivial thing, like this encoding of the elements is called tau, right? And so tau of 1 is equal to the identity. If tau of I is equal to p, then tau of minus I is equal to p the inverse. So like the trivial relations that you can check on elliptic curves like hold in this model. So, and then algorithms that act two oracles. One is that given I, you can get tau of I. And then there's an addition oracle that like will take an addition of 2 points for you because you can't compute it yourself, right? Because these are just random elliptic curve points that don't correspond to the group operation. So it kind of, the oracle implements the group operation for you.
What's C1 associated with what?
Yeah.
C1 was input to the black box, right? C1 is.
Oh, the constants. So this is just like saying like I can give 2 points and I can give C1 P. I can give like C1 P1 C2 P2 and I get C1 times P1 plus C2 times P2. So it's like you could exponentiate and yeah, affine, yeah.
You can't directly apply to the.
Right, because you don't know the representation. Yeah, 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 yeah. Okay. Oh, yeah, time. So, so we prove a theorem. I'm not, I mean, the details aren't super important, but we basically prove that in this model, CDL. So in this model, syntactically, this F sub ECDSA makes sense. And we prove that it's indeed hard to, I mean, we use techniques from the analysis of ECDSA actually to prove this, that that this problem is hard relative to the ECDSA conversion function. Okay, so I mean, and quantitatively, this is the same as, I mean, if the inverse, if the max preimage set of F is small, this like quantitatively, you get about Q squared over P, which is the same as discrete log. So quantitatively, the bound is about the same as discrete log. Okay. Yeah. Yeah.
The oracles is what here?
Yeah, so remember it's the mapping oracle and the addition, or I mean we're representing the group additively, so yeah.
Generic group model is a fact not group on dependence on credit. They capture what we expect to be more true in practice as a model. Like that's the because the adversary is weaker in those models, right? So we need to justify why.
Sorry, what's your question?
What the generic group model is trying to do is capture what the adversary would be able to do in practice.
Yeah. Yeah. So this is basically allowing, this is like augmenting the generic group model with some properties specific to elliptic curves, and to make it more realistic for elliptic curves. Yeah. Okay, and then there's like, so in the literature for ECDSA, they consider this thing called bijective ROM, which is basically, they kind of, even though F sub ECDSA is a very simple function, they introduce some idealization of it, which is basically, they represent it as like this composition of phi, pi, and psi. And it's basically like this models, I don't want to get into detail, but it models like kind of a function that is random, subject to the fact that it's like 2 to 1 and it has some properties of the ECDSA conversion function. And yeah, so I'll just skip this part. So let me wrap up and then I'll discuss some open problems which I think are interesting. I've been working on this direction. So we introduced the circular discrete logarithm problem and show a tight reduction from Schnorr to CDL in the ROM. We conjecture that the ECDSA conversion function will satisfy our new assumption. And we give evidence for that in idealized models. Some future directions are, is there a function for which CDL, so the interesting thing about this F is like you can construct it, right? And it can be based on some other assumptions. Like an interesting result would be even to use like obfuscation or something and construct some F, which in principle satisfies this CDL. I tried to do that, but didn't get very far, so. Yeah, and then I think I mentioned this earlier, but a tight reduction would not contradict impossibilities because the CDL is not generic. So the reduction computes F. So it's not a generic reduction. Then another direction I've been looking at is like, there's a lot of protocols that build on Schnorr, like, I don't know, multi-signatures, threshold signatures, blind signatures, adapter signatures, these kind of things. And it would be nice, they all inherit these problems of loose security. So it'd be nice to give tight results for them. So
How far have you gone in this one?
yeah, so we are like looking at threshold signatures right now, and it seems to probably work, hopefully. Yeah. And then another problem I'm very interested in, which I would love if anyone wants to discuss it, is like instantiating Schnorr signatures is an open problem. So can you give a concrete hash function for which you can prove that Schnorr is secure in the standard model, like even based on obfuscation or fully homomorphic encryption or anything you want. So this is no result, as far as I know, no result like that is known, and there's no impossibility result either. So it's like wide open. Yeah. So I mean, this is what my idea would be like, suppose we have F satisfying CDL, then can you wrap F in obfuscation or something like that to make it some H which makes Schnorr secure in the standard model, right? So CDL could maybe help you. Yeah. But I haven't been able to make it work. Okay, so the preprint is available and feel free to contact me. That's the end of the talk.